Hello everyone. So I'm going to talk about search for dark matter decay and annihilation using gamma ray observation by Tibet, gamma and LHAASO. This is the work based on these papers, and it is done with the collaboration with Tarak, Akash and Ranjan. So let's start. We know from the various astrophysical and cosmologic observation that most of the universe is made of dark matter. There's a huge mass range from like 10 to the power minus 22 electron volt to let's say 10 solar mass, and which people are trying to search for. I'm mostly gonna focus on this mass range around 10 to the power 6 PeV. There are various ways to detect dark matter. There's like direct detection, there are collider searches. I'm mostly gonna focus on something called dark matter indirect detection. There's one example of this you can see. So what can happen is dark matter can decay or annihilate and can produce, let's say, standard model particles, let's say W plus, W minus. And these particles can further decay and heteronize and can produce gamma rays. One other thing can also happen, these particles can also produce high energy electrons, and these high energy electrons can upscatter low energy background photon fields like CMB, starlight, infrared or extragalactic background light. And these will upscatter and produce something called inverse quantum gamma rays due to this inverse quantum scattering. The idea is to search for these gamma rays, these primary gamma rays or also these inverse quantum gamma rays in various detectors like LHAASO and Tibet gamma, and search for this dark matter decaying or annihilating signal. To do that, we first need to calculate the flux of these gamma rays. So let's consider the case of dark matter decay. So it depends upon this rho term. This is called dark matter density profile. This tells you how dark matter is distributed in our galaxy. Another term is this e to the power tau gamma gamma. This tells you that these high energy gamma rays can interact with low energy background photons, and that will reduce the overall flux of these high energy gamma rays. And this is given by this e to the power tau gamma. Another term is this DND. This is called intrinsic spectra of these gamma rays. This is coming from the fact this dark matter is decaying or annihilating to like various standard model particles, and the spectrum of gamma rays coming from these various standard model particles will be given by this term. For annihilation, the picture is almost the same, except the fact that since this flux of gamma rays for annihilation depends upon rho square, and if there is a dark matter substructure or dark matter subhalos, there will be extra boost factor coming from the fact since this substructure will form a local dense regions, and that will give you this boost factor in case of dark matter annihilation. I'll come to this term. In our analysis, we have taken into account both like primary gamma rays and inverse quantum gamma rays coming from like galactic and extragalactic region. And to calculating the boost factor, so you can see the boost factor another way you can define it like this. So this is the L host, and this is the luminosity of gamma rays coming from dark matter annihilation if there is no substructure, and this Lm is the luminosity if there is a dark matter substructure, and this is boost factor. You can calculate this boost factor by integrating over this subhalo mass function, like for a given mass of subhalo, how many number of subhalos will be there, and this LSH is the individual luminosity of these subhalos, and you can calculate this boost factor. The way we do this is we use a semi-analytic model to calculate this subhalo mass function and take into account effects like tidal disruption and all. And once you get this term, we can get this boost factor. You can see this in this plot. So what you see here is this boost factor as a function of host halo mass at a different redshift. So z equal to 0 or z equal to 6. Let's say this is the line for z equal to 6. One of the things you can notice from this plot is that at this lower masses of this subhalos, this boost factor is consistently going down if you go further in time. And so z equal to 6 is here, z equal to 0 is here. This is coming from the fact these lower masses of subhalos is losing their masses to like bigger halo or the host halos. So this is how this boost factor is going down for this lower masses of subhalos. Now, if we need to calculate this boost factor for, let's say, Milky Way, so Milky Way mass is around 10 to the power 12 solar mass, and this is the z equal to 0 line, you will get a factor of 5 to 6 boost in gamma ray flux for dark matter annihilation due to these substructures. So once we have calculated the flux for this gamma rays for both dark matter decay and annihilation, we can try to look for the observations. So for observations, we use two different detectors. One is this Tibet gamma, one is LHAASO. Both are extensive air shower detector. The way these detectors detect these gamma rays is that these gamma rays or cosmic rays comes and interact with atmosphere and produce this shower of secondary particles, and these secondary particles can be detected by detector at Earth, and then you can recreate the original particle here. And these detectors also have a muon detector, and this muon detector can help you differentiate between the cosmic rays and the gamma rays. The way you do that, you need to look at this air shower of these cosmic ray and gamma rays to see that. So if you look at this, if you have a gamma rays and this interact with atmosphere, it is mostly going to produce this electromagnetic shower. But if you have a cosmic ray and if it's interact with atmosphere, it can produce this particle like pi 0, pi plus, pi minus. And in the end of the day, they will also give you a muon. So if you have a muon detector, you can differentiate between this shower if it's coming from these gamma rays or if it's coming from these cosmic rays. Let's talk about the observation. So this was the first observation at sub-PeV diffuse gamma rays at these high energies. So what you see here, this Tibet gamma experiment has detected these diffuse gamma rays in two different regions in galactic disk. And what you see here, this is the flux of these gamma rays as a function of energy. And these three data points are observation by Tibet gamma. So this was the first observation at around this 10 to the power 6, roughly around PeV energies. And these dotted lines are various astrophysical background models. And these blue points are the previous observation at lower energies by an experiment called Argo by Vijay. And same thing is true for this different region. These lines are again theoretical predictions, and these blue dotted points are the upper limits, not the observation, by an experiment called Casimir. And these red data points are observation by Tibet gamma. And let's talk about LHAASO. So LHAASO have also detected these diffuse gamma rays, and what you see here is the flux of gamma rays as a function of energy, and these red data points are observation by LHAASO. This gray band is again a theoretical prediction, and they have also detected these gamma rays in a second region, this outer galaxy region. And what you see here in case of LHAASO, this red data points is roughly around 3 times what is the theoretical prediction is given by here. And in a different region, this is around factor of 2 times compared to the theoretical predictions. So since we are all talking about gamma rays at the galactic disk, what about the gamma rays coming from away from the galactic disk? Like dark matter is also there. I mean, we can also search for gamma rays away from the galactic disk. So we can do that, but we haven't found any gamma rays away from the galactic disk. But we can use this observation to put a limit on the gamma rays away from the galactic disk. And the reason we can do that is that these detector has a very good background suppression due to these muon detectors and all. And so you can see this upper limit in this plot. What you see here is this flux of these gamma rays as a function of energy. These different lines, these dotted lines, this straight line or this line, are the upper limits from other experiments, and these red lines are the upper limits from this Tibet gamma experiment, which are much better compared to these experiments. What we have done, we have used these like 3 observations to search for a dark matter signal or the excess in the observation. Since we haven't found any excess, we have put constraint on the decaying dark matter and the annihilating dark matter. So let's go. Yeah, so this is the constraint we have got. So this is the case of decaying dark matter. What you see here is the dark matter lifetime as a function of mass of this dark matter. And let's say we consider the observation by LHAASO, and this green line is the upper constraint. And so anything below this line is ruled out. So this is our anything below. So if we have a dark matter mass and a lifetime here, this is not possible. These dotted lines, these red lines and this orange line are the constraint from other experiment like ice cube and this KM2A. This is the part of LHAASO. These are the constraint from other experiments, and this line and this line is also our constraint. So we are able to probe a new region of parameter space here. This is also true if we consider a case of dark matter decaying to tau plus tau minus. We are able to probe a new region of parameter space in this region. For annihilating dark matter, this is again what you see here is the dark matter annihilation cross section as a function of mass. And these dotted lines are constraint coming from LHAASO dwarf galaxy. So LHAASO has tried to search for this high energy gamma rays coming from dwarf galaxy and then try to put constraint on dark matter annihilation cross section. What you see here, and so if in here anything above is ruled out. So anything of this line is ruled out. What you see here, these three lines which our constraint are much stronger than LHAASO's constraint, and this is also true for dark matter annihilating to tau plus tau minus, that this is constraint from LHAASO and we are getting much stronger constraint in a large region of parameter space. Okay, so we have obtained the constraint on dark matter lifetime and annihilation cross section. We have studied the effect of like inverse Compton scattering and dark matter substructure in our case, and we have found us like stringent constraint in the large region of parameter space for both decaying dark matter and annihilating dark matter. Thank you.
Thank you, Abhishek. So this session is now open for few questions. Yes.
So thank you for the very nice talk. Yep. So can you go, I have two questions.
Sure.
So one is, can you go to the plot for boost factor?
Yep. Yep.
Yeah, does the z equals to 0 line show a different behavior as compared to the other z lines?
Yeah.
So what can you say what's the reason?
So it's the behavior not necessarily need to be same, right? There are a lot of processes are going on, like there's tidal disruption, there are mergers and everything is going on.
Okay.
So this behavior need not be same as z equal to 0 compared to z equal to 6.
Okay, thanks. And my second question is regarding the this tau constraint. Can you go to that plot?
Yeah.
So the dotted line, so we see that for lower masses, it kind of increases, but it so the dotted line, the left hand side plot, dotted line. So chi going to BB bar.
Yeah.
So we see that for lower masses, it is increasing, but after a certain mass, it starts to saturate. Can you explain that behavior? Why is this happening?
I mean that depends upon the observation. This is coming from the ice cube, right? So
for the same plot I'm talking about.
Yeah, the same plot. So,
yes.
So this is not our constraint. This is taken from this ice cube measurement.
Okay.
So they have tried to search for neutrinos, and you can use these observations. So depending upon where you they have tried to search for this neutrino, you will get constraint according to that. So
Okay. Thanks.
Sure.
Thank you, Abhishek, for this nice talk.